Forty speaking. We're going to be going over Chapter 9 today. Okay. One thing to keep in mind is for Chapter 9 is when you are doing some of these assignments and the content, Chapter 9 is actually just a repeat of Chapters 7 and 8. So a lot of methods you'll be doing Chapter 7 and 8 will repeat for Chapter 9. The difference is Chapter 7 and 8 focuses on proportions, while Chapter 9 focuses on mean and standard deviation. So let me kind of give you an example. I'm going to kind of go over 9.1 and 9.2 examples. Okay, so as an average income, here's the problem for the following. Okay, and then it says suppose standard deviation is 30,000 and distribution is right skewed. Suppose we take a sample of 400 students in Connecticut. So we have to remember, right, there's specific letters that goes for these, right? So 60,000. Now let's talk about what is 60,000. It is average. Actually, sorry, let me zoom in. So 60,000 here in our regards is average, but it's average out of all of Connecticut. So we're doing mean, but we're doing mu. Okay, why is that? Because this is the mean of the population. Okay, so it's not X bar. X bar is sample mean. Okay, and then what is this 30,000? It is standard deviation. So standard deviation here is, we have to be careful. So there's two standard deviations, right? There's S and there's sigma. We're going to do sigma because this one's talking about standard deviation. For mean. Sorry, for population. Okay? So what value should we expect for the sample mean, right? We expect 60,000, right? Because that's the mean of my population. Okay? Okay, but obviously remember, right, if I do a sample, right, I will have what's called a standard error. Okay, now your standard error for Chapter 9 is a little bit different. Okay, so let's remember this. Okay, so when you're doing proportion, right, your standard error is the following, right? It is square root p times 1 minus p over n. Okay. We are not doing that one, right? Because we are talking about mean, okay? So since I'm doing mean, I'm trying to do standard error. The one I'm going to be using is sigma over square root of n, okay? And then remember, sometimes we do S over square root of n if sigma is not given. Okay. Just like the following, right, we use p hat 1 minus p hat over n if p is not given. Okay. Okay. So be really careful, right? So when they ask you to find standard error, ask yourself, are you talking about standard error for proportion, or are I doing standard error for mean? Okay, so that's really important to take in mind. Okay. So in our case, we're doing sigma over square root of n. So if I look back up here, my sigma is 30,000 and my n is 400. So my standard error, which is sigma over square root of n, is equal to 30,000 divided by square root of 400. Right, so I put this in my calculator here. And I get 1,500. Okay, so my standard error is 1,500. That's my final answer here. Okay. So Let's talk about a couple other things right here. Okay. So let's talk about this for the following. I'm going to talk about section 9.2 right here. Sorry. So let's remember, so when we say mu, we're talking about this, okay? So one of the things is you want to actually understand, okay, the following. You want to understand all the different types of letters, right? So let's talk about this, right? So it says a mean age of all 22,550 students is 22.8 years, okay? So this right here is mu, okay? So that's actually my answer, right? So why? Why is mu? So why is it 22.8? Because it is the mean for my population. And remember, so since it's a population, we're talking about parameter, okay? It's parameter because it describes population, okay? Let's just remember the following, okay? Parameter describes population, statistic describes sample, okay? And then, so that means this one is sigma, okay? Sorry, this should be mean. That's a little bit of a typo. A random sample of 4 years is obtained, and the mean is 23.2 with standard deviation of 2.4. So what does this mean? This mean is X bar because we're doing sample mean. And this one's S. So this one is sample standard deviation. Okay. Okay, so just make sure you remember your 6 letters. So remember the other 2 is P hat and P. So remember, right, look at what you're describing the population, or you're describing the sample, and then what are you describing of the sample or population, right? So there's 2 attributes you have to kind of know, right? So remember you have mean population, which is mu, standard deviation population, which is sigma, sample mean, which is X bar, sample standard deviation, which is S, P, which is population proportion, and P hat, which is population, P hat, which is sample proportion. Okay. Okay. So let's talk about this in part B. Okay. So there is also central limit theorem conditions as well. So let's talk about this right here. So let me talk about this. So central limit theorem for proportions. We're not doing this, but I want you to remember kind of what are the criteria, right? So remember, criteria is simple random sample. We assume n times p is greater than 10. N times 1 minus p is greater than 10. And then the third one is population is greater than 10 times n, okay? So central limit theorem for means, okay, yeah, so we have to be very careful. There are 2 different conditions, central limit theorem conditions for proportions, and then you have central limit theorem conditions for means. So the first one is simple random sample, which we do have. The second one is actually going to be just n is greater than 25, okay? And the third one will also be the same. So there is some slight variance for the following here, okay? So let's talk about this. So part B, if we have a sample of 4 students, right, notice we actually violate the second rule. The second rule means my sample must be greater than 25, okay? Why is this important? So the idea is you want to actually have a large sample size, okay? Because if you don't, you can't use central limit theorem. And remember, what does central limit theorem do? Central limit theorem, what it does is it takes any distribution and normalizes it. So even if I have a skewed left, skewed right, symmetric, whatever, at the end of the day, if I have central limit theorem, if all my conditions are met, what I would do is I would take central limit theorem and it makes the curve normalize, right? Normal means, right, it's unimodal and it's symmetric on both sides. But because I have a sample of only 4 students, I can't apply central limit theorem. So because it's right skewed, it's going to stay right skewed, okay? Now, if I have a sample that's like 100, what it's going to do is it's going to turn it normal, and then we can use central limit theorem. But here I can't do anything because my central limit theorem is not fulfilled for the following. Okay. So let me show you one last example for okay. Yeah, let's look at this one here. So this is the last problem for section 9.2. So the average income in the District of Columbia in 2013 was $76,000 per person per year. Suppose the standard deviation is 35,000 and distribution is right skewed. Suppose we take a random sample of 100 residents of DC. Okay, so this is what we're going to do. Okay, so we're going to try to see if we can use central limit theorem, right? Simple random sample, which it does, right? It says it right here. Second rule is n is greater than 25. Yes, right, because I have a sample of 100. Okay. And then a third rule is the following. Okay. I'm going to see if my population is greater than 10 times n, or in this case, 10 times 100. Okay. Now here's the thing. I don't know the population of DC, but I'm pretty sure it's larger than 1,000. Okay. So we would say yes, right? We can use central limit theorem. Okay. So it doesn't matter. So the idea is because it's right skewed, even though it's right skewed, I can use a central limit theorem, and the idea is it's going to turn normal. Okay, because of central limit theorem. So they ask you next, what is the mean and the standard error, okay, of the sampling distribution? So your mean in this case, right, is 76,000. And your standard error, right, remember you're going to use a formula, which is sigma over square root of n, okay? Now, this one is sigma, right? This one is mu, okay? So this one's going to be 35,000 divided by square root of 100, and that is equal to, it's really just dividing by 10, so it's just going to be 3,500. So that is your SE, okay? Okay, so let's look at this last part C. So it says, what is the probability that the sample mean will be more than 3,500 away from the population mean, okay? So remember, because of central limit theorem, we normalize our curve. And so let me sketch this right here. So in the center is going to be 76,000, right? And I'm going essentially up and down by 3,500. So this is 79,500. This is 83. And this is 86,500. This is 72,500. This is 69,000. This is 65,500. Okay, so now if they're saying more than 3,500, they're actually talking about this. Okay, so there's actually a couple ways to do this, right? We're actually finding an area under both of them. Thankfully for us, it actually lands on a hash mark. So if you remember, right, think about your 1, 2, 3 rule. So if you think about this, right, this is 68%, right, because that's one standard deviation. And if remember, you're going to do 100 minus 68, that'll be 32%, okay, for the following. Okay. Now, you could also find an area, right, using what's called the z-score, right? So the z-score is now is observed minus mean over standard deviation, okay, or standard error, standard deviation. We have to be really careful because this time our observed is going to be, right, is my, let's see, my x bar minus my mu over sigma over square root of n, okay? So you can go that route as well, okay? Now we don't have enough information, but later on we'll talk about this. This will be used quite a bit, okay? But yeah, make sure you know all your different formulas. Okay, it's starting to ramp up quite a bit. If you have questions, send me an email or you can post on the discussion board. Other than that, I'll see you guys later.